Module 4, Lecture B, Gradient Descent. By the end of this lecture, you will be able to explain gradient descent as repeated parameter adjustment to reduce prediction error, implement batch and stochastic gradient descent for linear regression from scratch, and analyze learning curves to diagnose slow learning, divergence, and reasonable convergence. Minimizing prediction error. Error minimization. Gradient descent improves a model by starting with imperfect parameters, comparing predictions with actual results, and adjusting the parameters to reduce error. In linear regression, this helps the model find the line or plane that best fits the data. Over repeated updates, the model uses prediction errors as feedback to become more accurate. A regression model improves by combining its individual prediction errors into one loss value. This loss shows how well the model is performing across the dataset. When parameter changes lower the loss, the model is improving. When they raise it, performance is getting worse. The goal is to keep producing loss so predictions move closer to the actual outcomes. Gradient descent reduces prediction error by repeatedly adjusting a model's parameters in the direction that lowers the error. The model does not understand the real-world meaning of the data. It simply changes numbers to make predictions closer to actual outcomes. Through this steady process of correction, the model gradually improves. Python code, error minimization. This script demonstrates error minimization by showing how a line is improved through repeated corrections. Loss is used to measure the overall prediction error. The script begins by importing NumPy for efficient array handling and mathematical operations, along with Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the code for data manipulation and visual output. A fixed, random seed is set, so the results are reproducible each time the code runs. The data then defines mechanical loads from 1 to 6 kilonewtons and matching deflection values in millimeters. Because these deflection values are predefined rather than random, they provide known data for testing the model. Before modeling, confirm that the load and deflection data are each one-dimensional and have the same length. This ensures every load value matches a corresponding deflection value, helping catch data mismatches early and preventing errors in later calculations. We start gradient descent with an initial straight line. The slope is set to 0.2, the intercept to 0, and the learning rate to 0.04. These starting values guide how the line is adjusted step by step to reduce the error between predictions and the actual data. We prepare gradient descent by setting up a record of error values, choosing 40 update steps, and counting the number of data points. These values let us track learning progress, control how long the model trains, and compute averages correctly during optimization. The model is trained by repeating a set number of updates to reduce prediction error. In each step, it predicts deflection from the current slope, intercept, and load values, then compares those predictions with the actual deflections. The average squared error is used as the loss, showing how far the model's predictions are from the data. We record the current loss to track how the error changes during training. Then we compute gradients for the slope and intercept from the errors, showing how each parameter should change to reduce the loss. Finally, the slope is updated by moving it opposite the gradient, scaled by the learning rate, which is the basic idea of gradient descent. In gradient descent, the intercept is adjusted by subtracting the learning rate times the intercept gradient. This update moves the intercept in the direction that reduces prediction error. helping the model improve its accuracy over repeated iterations. Using the learned slope and intercept, we predict deflection for each load value. We then compare these predictions with the actual deflections using mean-squared error. This final loss shows how well the adjusted model fits the data. We compare the initial loss with the final loss to see how much gradient descent reduced the error. Then we report the learned line using its adjusted slope and intercept, which represents the best fit to the observed data. A matplotlib figure is set up with two side-by-side plots. In the first plot, the observed load and deflection data are shown as a scatter plot. Then a red line is added to show the learned linear relationship. This makes it easy to compare the model's fit with the actual data. The first subplot is labeled to show load in kilonewtons on the horizontal axis and deflection in millimeters on the vertical axis. A legend identifies the observed data and the learned line. The second subplot shows the loss history as a purple line, illustrating how the error changes during gradient descent. The plot is labeled to show how mean-squared error changes across gradient descent steps. Its title emphasizes that repeated parameter adjustments reduce the error over time. The layout is tightened to prevent overlap, and the plot is then displayed for analysis. This script uses gradient descent to fit a line to mechanical test data. Starting from a rough slope and intercept, it repeatedly adjusts them to reduce the mean-squared error between predicted and measured deflection values. The results show the error decreasing and the final line closely matching the data, demonstrating effective error minimization. Weight updates. In linear regression, gradient descent updates the model's weights by using prediction errors as feedback. After comparing predictions with actual values, the model makes small adjustments to reduce future error, lowering weights that push predictions too high and raising those that make them too low. Repeating this process gradually improves accuracy. The gradient shows how changes to a weight affect the error, guiding updates in the direction that reduces it. If a change makes the error worse, the update moves the other way. If it improves the error, it continues in that direction. In regression, the learning rate controls how large each update is. Smaller rates move carefully, while larger rates can overshoot the best values and increase error. Repeated weight updates help a regression model better match patterns in the data. Gradient descent makes small adjustments to reduce prediction errors, such as increasing the influence of apartment size when larger apartments are underestimated. As the model improves, these updates become smaller, using error as a guide toward better accuracy. Python code weight updates. Weight updates use prediction errors to improve the model. With a tiny rent dataset, the calculations stay easy to follow as each update slightly adjusts the slope and intercept. We import NumPy to work efficiently with numerical data in arrays and matrices. We also import Matplotlib's plotting tools to visualize data trends and calculation results. We store apartment sizes and their monthly rents as separate NumPy arrays so the data can be handled efficiently. These arrays provide the basis for modeling how apartment area relates to rent. The code scales both apartment areas and rent values by dividing them by 1,000. This keeps the numbers smaller and more consistent, which makes calculations easier and helps gradient descent learn more stably. Before training, confirm that the input and output values are one-dimensional and have the same number of elements. This ensures each area value matches one rent value, keeping the dataset consistent for a simple linear relationship. We start the model with imperfect initial settings so it can learn during training. The weight begins at 0.2, setting the line's starting slope, and the bias begins at 0.8, setting its starting intercept. The learning rate is 0.25, which controls how large each adjustment is, with smaller values usually making updates more stable. We initialize 2 empty lists to track training progress during gradient descent. One stores the mean squared error at each iteration, showing how the loss changes over time, while the other records the weight values as they update. Together, these histories help visualize the learning curve and understand how the model improves. The loop runs 12 batch gradient descent updates. In each pass, the model predicts rent by using the current weight, scaled area values, and bias. It then compares those predictions with the actual rents to find the errors, which guide later adjustments to the model parameters. Mean squared error measures prediction error by averaging the squared differences between predicted and actual values. We record this loss over time to track how the error changes, and we also record each weight value to see how the weight evolves during updates. The code computes gradients for the weight and bias, so gradient descent can update the model. The weight gradient is based on the average relationship between the errors and the scaled input values, while the bias gradient is based on the average error alone. Together, these gradients show how to adjust the parameters to reduce prediction error. The model updates its weights and bias by moving them in the direction that reduces prediction error. This is the core idea of gradient descent. Repeated small adjustments help the model learn from its mistakes and improve accuracy over time. We compare the initial and final loss to see how much the prediction error decreased during training. We also report the learned weight and intercept, which are the final parameter values after all updates. Overall, the process shows how repeated adjustments based on current error improve the model. This plot shows how prediction error changes as the model's weights are updated. It graphs mean squared error against the weight update number, using markers for each recorded point. Clear axis labels, a title, and a light grid make the trend easier to read, helping us see whether the error decreases over successive updates. This script uses batch gradient descent to train a simple linear regression model that predicts apartment rent from area. Starting with imperfect slope and intercept values, it repeatedly adjusts them based on prediction errors, with the learning rate controlling the size of each update. As training continues, the mean squared error decreases, showing that the model is improving. The script reports the initial and final loss, the learned parameters, and a plot of the error reduction over time. Loss landscape. Gradient descent finds better model parameters by treating error like a landscape to move through. Instead of trying every possible setting, it uses the slope at the current point to choose a direction that lowers the error. By taking repeated steps toward lower error, the model gradually improves. In linear regression, the error surface is usually smooth and bowl-shaped, making gradient descent easy to understand. The gradient points toward increasing error, so the model updates its parameters in the opposite direction, moving downhill toward the lowest error. This minimum represents the best parameter values for reducing prediction mistakes, using the gap between predicted and actual values as feedback. The loss landscape shows why both the size and direction of parameter updates matter. Steps that are too small make learning slow, while steps that are too large can overshoot and increase error. Gradient descent aims to reduce error by following the local slope, even in complex landscapes. Python code, loss landscape. Think of loss as a landscape shaped by the model's parameters. In linear regression, those parameters are the slope and intercept, and lower points on the landscape represent smaller prediction error. We import NumPy for efficient numerical work with arrays and calculations, and Matplotlib's PyPlot for creating graphs and charts to visualize data. A random seed is set, so random operations give the same results each time, supporting reproducibility. Then a set of force values from 10 to 60 newtons is created as floating point data for a mechanical calibration dataset. Deflection in millimeters is first modeled as a linear response to force in newtons, using a fixed slope and starting offset. Small random noise is then added to represent real measurement variation. The result is a more realistic set of deflection values that still follows the overall linear trend. Before modeling, confirm that the force and deflection data are both one-dimensional and have the same number of values. This ensures each force measurement matches one deflection measurement, which is necessary for accurate calculations and error analysis. To test different settings for a linear regression model, we create candidate values for the slope and intercept across chosen ranges. The slope values run from 0.25 to 0.60, and the intercept values run from -2 to 6. We then form a grid of every slope and intercept combination, so the model's loss can be evaluated across many possible parameter settings. For each slope and intercept pair, we predict deflection from the force values, then compare those predictions with the actual deflections. The differences are squared and averaged to produce a mean squared error. This loss value shows how well each slope and intercept combination fits the data. To find the best linear regression parameters, we locate the smallest value in the loss array, which represents the lowest mean squared error. That position is converted into the matching location on the slope and intercept grid, allowing us to extract the optimal slope and intercept. Together, these values identify the point on the loss landscape where the model error is minimized. The output reports the best slope in millimeters per newton, the best intercept in millimeters, and the lowest mean squared error, using clear rounded values. These results show the model parameters that produce the smallest error. The explanation then connects this to gradient descent, which works by moving toward regions of lower error during optimization. We create a Matplotlib figure and axis, then use a filled contour plot to show how loss changes across different slopes and intercepts. The plot uses a smooth color map with multiple levels to make the loss landscape easier to read. A color bar is added to show the mean squared error values represented by the colors. The plot highlights the best linear regression parameters by marking the optimal slope and intercept with a visible red dot. The axes are labeled to show slope in millimeters per newton and intercept in millimeters, and the title identifies the visualization as the loss landscape for linear regression. Finally, the code uses the Matplotlib show function to display the contour plot of the loss landscape. This lets us see how different slopes and intercepts affect the mean squared error, helping us understand which parameter combinations perform better in the linear regression model. This script shows how a linear regression model finds the best fit for force and deflection data. It tests many possible slopes and intercepts, calculates the mean squared error for each pair, and identifies the combination with the lowest error. A contour plot then displays the loss landscape and marks the optimal parameters, helping illustrate how gradient descent moves toward the minimum error region. Descent variance. Batch gradient descent Batch gradient descent trains a linear regression model by using the entire dataset before making each parameter update. It predicts all training examples, compares them with the actual values, and then adjusts the intercept and weights to reduce the average error. Because each update is based on all examples, the model improves overall performance rather than reacting to one data point at a time. Batch gradient descent updates model parameters by using predictions and errors from the entire training dataset at once. A learning rate controls the size of each adjustment. Because every update is based on all examples, the method is stable, but it can be slow and costly for very large datasets. Effective batch gradient descent depends on well-prepared data and careful monitoring. Scaling features is important when their units differ widely, and checking the loss after each full pass through the data shows whether learning is working. A steadily falling loss suggests progress, while a flat or rising loss may point to problems with the learning rate or scaling. This makes the training process more transparent by linking prediction errors to parameter updates. Python code. Batch gradient descent. Batch gradient descent updates all model parameters at the same time. In this example, scaled apartment features are used, and the learning curve shows how the model converges during training. The script begins by importing tools for numerical work and visualization. NumPy supports efficient array handling and calculations, while Matplotlib's plotting module is used to create charts and graphs. Together, they prepare the environment for later data analysis and plotting tasks. We create reproducible apartment data using NumPy's random number generator. Setting the seed to 7 makes the same random values appear each time the code runs, which helps with debugging and consistent results. We generate random apartment data to use as features for predicting rent. The dataset includes 80 values for apartment size, 80 values for number of bedrooms, and 80 values for distance from a central point. These 3 feature columns provide the basic inputs for the rent prediction model. The apartment features are combined into one design matrix by placing area, bedrooms, and distance side by side as columns. This creates a data table with 80 apartments and 3 features for each one. A shape check confirms the matrix is organized correctly before further processing. The dataset adds realistic variation to rent prices by generating normally distributed noise with mean 0 and a standard deviation of 90. Rent is then modeled from a base price of $450, increasing with apartment area and number of bedrooms, and decreasing with distance from the city center. Adding the noise to these calculated rents creates a more realistic set of simulated rent values. Before using gradient descent, each feature is standardized by finding its column mean and standard deviation. The mean is subtracted from each value. Then the result is divided by the standard deviation. This centers the features around 0 and gives them unit variance, helping gradient descent converge more quickly and reliably. To add an intercept to the model, create a column of 1s and attach it to the scaled feature data. This gives every data point a constant tone, allowing the model to learn an offset. Then confirm that the new feature matrix has the same number of rows as the target values. We initialize the model by setting all parameters, including the intercept, to 0. We then choose a learning rate of 0.08 and train for 120 epochs, meaning the full dataset is used repeatedly to update the parameters. An empty loss history is also created to record the mean squared error after each epoch and track performance over time. In batch gradient descent, Each epoch uses the current model parameters to predict rent values from the design matrix. The model then compares these predictions with the actual rents to compute errors and calculates the mean squared error as the loss. This loss is stored after each epoch, so we can track how performance changes during training. Batch gradient descent first computes the loss gradient from the design matrix and the error vector, showing how the loss changes with the parameters. The parameters are then adjusted by subtracting the learning rate times this gradient. This single update moves them in a direction that reduces the loss. To convert scaled model coefficients back to the original feature units, divide each feature weight by its corresponding standard deviation. Then adjust the intercept by starting with the scaled intercept and subtracting the combined effect of the feature means and standard deviations. This restores both the weights and intercept, so the model matches the original data scale. The output summarizes a rent prediction model by first noting the NumPy version for reproducibility, then comparing the mean squared error before and after training to show improvement. It also reports the learned intercept and feature weights, showing how area, bedrooms, and distance from the city center affect predicted rent. Together, these values describe both the model's performance and the influence of each input feature. This plot shows the learning curve for batch gradient descent by graphing mean squared error over full dataset updates. The loss history is drawn as a clear line, with labeled axes, a title, and a light grid to make the trend easy to read. Displaying the curve helps diagnose whether the model's error is decreasing and whether the training process is converging. This example shows how batch gradient descent can train a linear regression model to predict apartment rent from features such as area, bedrooms, and distance from the city center. It uses synthetic noisy data, scales the features for stable learning, and repeatedly adjusts the model to reduce mean squared error. As training progresses over 120 epochs, the error decreases, showing convergence. The final results report the starting and ending errors, the estimated feature effects in original units, and a learning curve that confirms the model is improving. Stochastic gradient descent. Stochastic gradient descent updates a model after each training example instead of waiting for the full dataset. In linear regression, it makes a prediction for one observation, compares it with the true value, and adjusts the parameters to reduce error. Because examples are often shuffled, this randomness can help learning move faster, especially with large datasets. In stochastic gradient descent for linear regression, each training example is used to make a prediction, measure the error, and slightly adjust the intercept and weights. If the prediction is too high, the model is nudged downward. If it is too low, it is nudged upward. The learning rate controls the size of these updates, so it must be balanced to avoid unstable jumps or very slow progress. Over time, many small updates help the model improve, such as when new delivery data refines delivery time predictions. Stochastic gradient descent updates the model using one example at a time, making it efficient but sometimes noisy. The loss may rise and fall, so focus on the overall downward trend rather than a smooth curve. Shuffling the data helps prevent order-based patterns, and the main idea is to make frequent small updates instead of waiting for the full data set. Python code, stochastic gradient descent. This lesson demonstrates stochastic gradient descent from scratch using a tiny delivery dataset for regression. It focuses on how the model updates its parameters one example at a time. producing noisy but useful changes. The key comparison is between these noisy individual updates and the overall loss measured across each training epoch. We import NumPy to handle the numerical array operations needed for gradient descent. We also import Matplotlib's plotting tools so we can visualize the stochastic gradient descent learning curve and see how model performance changes over time. We set the NumPy random number generator with a seed of 7, so later random actions are repeatable. This makes results consistent across runs, which helps with debugging and comparing outcomes. We create a small set of delivery distances in kilometers using values from 1 to 8 stored as floats. This gives the regression model consistent numeric input for predicting delivery times. A NumPy array is created to store delivery times as floating point values. These times increase with delivery distance, forming the target data for a regression model that predicts delivery time from distance. Before running regression analysis, confirm that the delivery distances and delivery times are both one-dimensional arrays with the same number of values. This ensures each distance is matched to one delivery time, so the analysis is based on correctly paired data. We standardize the delivery distance feature to make gradient descent more stable and efficient. This means centering the data by subtracting its mean, then scaling it by its standard deviation, so the values have a consistent range. To prepare data for linear regression, add an intercept term to the design matrix by placing a column of ones next to the standardized features. This lets the model learn a constant offset, as well as the slope, which is needed to predict delivery times from distances accurately. This function measures model accuracy using mean-squared error. It first generates predictions from the design matrix and parameter vector, then compares them with the actual values to find the errors. By averaging the squared errors, it returns one floating point value that summarizes the model's prediction performance. The stochastic gradient descent function begins by setting up the values needed for training. It creates an initial parameter vector filled with zeros, prepares a place to record loss after each epoch, and counts the number of data points. This setup allows the algorithm to update the parameters one data point at a time to reduce prediction error. The training process repeats over several epochs, with each epoch making one full pass through the dataset. At the start of each pass, the data is shuffled, so updates happen in a random order. For each example, the model predicts using the current parameters, measures the error against the true target, and adjusts the parameters using the learning rate to reduce that error. After each epoch, the mean-squared error is recorded to track how the model improves over time. The function returns the learned model parameters after stochastic gradient descent, along with a record of the loss after each epoch. These loss values are mean-squared errors, and they show how the model's error changes during training. Together, the outputs indicate both the final coefficients and how effectively the updates improve the model. The learning rate is set to 0.04, which determines how strongly the model updates its parameters each time. The model is trained for 35 epochs, meaning it makes 35 full passes through the dataset to gradually refine what it learns. We run the stochastic gradient descent function without printing intermediate output. It uses the design matrix, target delivery times, learning rate, and number of training epochs to learn the model parameters. The design matrix includes the standardized feature and an intercept term, while the learning rate controls update size and the epochs control how many passes are made through the data. The function returns the final parameters and a loss history showing how the error changed during training. To express the learned linear model in the original distance units, convert the standardized slope by dividing it by the original distance standard deviation. Then adjust the intercept by subtracting the adjusted slope times the original distance mean from the standardized intercept. This gives both the slope and intercept on the original scale. The output first confirms the NumPy version for reproducibility, then reports the learned linear model using its intercept and slope. It also compares the mean squared error from the first and final training epochs to show how performance changes. Although stochastic gradient descent loss can fluctuate, the overall trend should decrease, indicating that the model is learning. This plot shows the learning curve for stochastic gradient descent across training epochs. It graphs the recorded mean squared error for each epoch, using markers to make individual results easy to see. The axes and title identify the epoch count and error metric, while a light grid and adjusted layout make the chart easier to read and interpret. This example shows stochastic gradient descent learning a simple linear relationship between delivery distance and time. The data is standardized, an intercept is added, and the model parameters are updated repeatedly using shuffled data each epoch. As training progresses, the mean squared error generally decreases, showing that the model is improving. The final results report the learned line and compare the error from the first and last epochs, while the learning curve shows a noisy but downward trend. Epoch updates. An epoch is one complete pass through the training data during gradient descent. In batch gradient descent, the model uses the whole dataset to make one overall parameter update. In stochastic gradient descent, it visits each example once, often in shuffled order, and makes many small updates. This helps compare training progress across different gradient descent methods. When building gradient descent from scratch, epochs define the outer training loop, while parameter updates handle the inner work of reducing prediction error. In stochastic gradient descent, it is important to shuffle the data at the start of each epoch, so the model does not learn from a fixed or biased order. This helps make updates more balanced, especially when the data is sorted in a way that could skew training. Monitoring each epoch shows whether training is progressing well. After every epoch, compare training and validation error. Steadily falling error suggests the model is learning. Little change may point to a low learning rate or weak features, and sudden spikes can mean the learning rate is too high. In short, smooth improvement is a good sign, while unstable error signals that training settings may need adjustment. Python code. Epoch updates. Epochs group repeated gradient descent updates into full passes of training. Batch and stochastic methods differ in how often they update the model, and learning curves show progress across epochs. The script begins by importing NumPy for efficient numerical work with arrays and calculations, and matplotlib pyplot for creating graphs. Together, these libraries provide the basic tools for data manipulation and visualization. We create a NumPy random number generator with a seed of 7, so the generated numbers are reproducible. This means the same random sequence appears each time the code runs, which helps with debugging and consistent comparisons. We generate 24 evenly spaced beam lengths from 1 to 6 meters using NumPy's linear spacing function. These values form the feature input for the model. The target deflection in millimeters is generated from each beam length by starting with a base value of 2.5 and adding 1.8 times the length. Random normally distributed noise with mean 0 and standard deviation 0.35 is added to each value to simulate realistic measurement variation. The code validates the training data by checking that the features and targets have matching shapes and that the dataset has more than 2 samples. This helps ensure the data is suitable for basic statistical analysis and model training, reducing the chance of errors later. To normalize a feature, first find its mean and standard deviation, which describe the data's center and spread. Then subtract the mean from each value and divide by the standard deviation, giving the feature a mean of 0 and a standard deviation of 1. This standardization helps gradient descent update more smoothly and learn more reliably. The mean squared error function measures how accurate the model's predictions are. It uses the current intercept and slope to make predictions, compares them with the actual target values, and measures the average squared difference. This gives a clear score for how well the model fits the data. This calculation finds the mean squared error by comparing predicted values with actual values, squaring the errors, and taking their average. The result is then converted to a float to keep numerical operations consistent. The batch gradient descent function trains for a set number of epochs, starting with both weights set to 0. During training, the weights are updated to reduce error, and the mean squared error is recorded after each epoch to track performance over time. During each epoch, the model makes predictions using the current weights, feature values, and intercept. It then compares those predictions with the actual target values to find the errors. These errors guide the gradient descent updates to improve the weights. In gradient descent for a line, we compute separate gradients for the intercept and the slope. The intercept gradient is based on twice the average prediction error, while the slope gradient is based on twice the average of each error multiplied by its feature value. These gradients show how to adjust the model parameters to reduce the overall error. The code performs gradient descent by updating the intercept and slope weights. Each weight is reduced by the learning rate times its error gradient, helping the prediction line move toward lower overall error. The code records the current mean squared error after each epoch by evaluating it with the current weights and training data. This loss history shows how the error changes during training. The function then returns both the final weights and the recorded losses as a summary of the training process. We define a stochastic gradient descent function that runs for a chosen number of epochs. The model starts with both weights set to 0, and it records the loss after each epoch so we can track how performance changes over time. A local random number generator is created with a fixed seed, so results are reproducible each time the code runs. The code then finds the number of samples from the input feature data, which supports dataset operations such as shuffling, indexing, and stochastic gradient descent. Each epoch is one full pass through the dataset. At the start of each epoch, the sample order is randomly shuffled using NumPy's random permutation method, so the model sees the data in a different sequence each time. This randomness supports stochastic gradient descent by adding variation to the updates and reducing the chance of getting stuck in a local minimum. For each shuffled data point, the loop uses the current weights and feature value to predict the target. It then compares this prediction with the actual target by calculating the error. That error shows how far the model is off and guides the next weight update. This code updates the model weights during stochastic gradient descent. It adjusts the intercept by moving it against the current error, scaled by the learning rate. It then updates the slope using the learning rate, the same error, and the current feature value, helping the model better fit that data point. The code records the current mean squared error after each epoch by evaluating it with the current weights and training data. This loss history shows how the error changes during training. The function then returns the final weights along with the recorded losses. The model is trained for 25 epochs using both batch gradient descent and stochastic gradient descent. Each method uses the same scaled features and target values, but different learning rates, with stochastic gradient descent also using a fixed random seed for reproducibility. Both training runs return final weights and mean squared error losses, allowing their convergence and performance to be compared. The output first reports the NumPy version and dataset size to confirm the setup and give context for the data being processed. It then compares how often the two gradient descent methods update the model. Batch gradient descent updates once per epoch using the full dataset, while stochastic gradient descent updates once for each data point. Finally, it prints the final mean squared error for both methods, allowing a quick comparison of how well each reduced the error after training. This plot compares the training progress of batch gradient descent and stochastic gradient descent across epochs. It shows each method's training mean squared error with different markers, labels the axes for epoch and training error, and includes a title, legend, and subtle grid for readability. The final layout presents a clear visual comparison of how both methods reduce error during training. This script compares batch and stochastic gradient descent on a scaled beam deflection dataset. Batch gradient descent updates the model once per epoch, giving smoother convergence, while stochastic gradient descent updates after each data point, producing faster but more erratic changes. Both methods are evaluated with mean squared error over 25 epochs, and their final errors and learning curves show the trade-off between stability and frequent updates. Convergence checks. Learning curve trends. A learning curve shows how a model's error changes during training, helping you judge whether gradient descent is improving the model. In linear regression, it tracks loss after data passes or parameter updates. The curve should generally move downward, even if it is not perfectly smooth, because that means prediction errors are decreasing over time. Early in training, a model's error often drops quickly because its parameters are far from optimal, so updates make large improvements. As the model gets closer to a good solution, each update helps less, and the error curve flattens. This plateau can be normal if the model has reached stable low error, but it may also mean learning has stalled too soon. When reading learning curves, focus on the overall trend rather than small fluctuations. Check the scale and noise, and compare results across training runs, since a flat-looking curve may still be improving and jagged movement can be normal, especially with stochastic gradient descent. Batch gradient descent usually gives smoother curves because it uses the full dataset. A curve that steadily falls and levels off suggests convergence, while one that stays high or unstable needs further investigation. Python code. Learning curve trends. Learning curves help show how gradient descent is behaving during training. This example uses small synthetic beam data to compare healthy training with slow learning and divergent training. The script begins by importing NumPy for efficient numerical work with arrays and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the environment for later data analysis and plotting tasks. We set a fixed random seed of 7 for NumPy's random number generator. This makes the random results repeatable each time the code runs, ensuring consistent and reproducible output. We generate 80 synthetic data points for a mechanical engineering feature, beam length in meters. The values are randomly sampled from a uniform range between 1 and 5 meters, giving a realistic spread of possible measurements. Random noise is generated with an average of 0 and a standard deviation of 0.8 to represent measurement error or natural variation. Deflection values are then simulated using a linear relationship, a base value of 2.5 plus 3.2 times each sample length, with the random noise added in. First, check that the length and deflection measurements have matching shapes, so each value can be paired correctly. Then confirm that the stated number of samples matches the actual size of the length data. These checks keep the data consistent and help prevent errors in later calculations. To standardize the length measurements, first find their average using NumPy's mean function. Then find their spread using NumPy's standard deviation function. Each value is adjusted by subtracting the mean and dividing by the standard deviation. This gives the data a mean of 0 and a standard deviation of 1, which helps gradient descent update more stably. We prepare the regression data by adding an intercept column of 1s, allowing the fitted line to avoid being forced through the origin. This intercept is combined with the standardized feature values to form the design matrix, where rows represent samples and columns represent model inputs. The noisy deflection measurements are then used as the target values for the regression model. The mean squared error function measures prediction accuracy by comparing a model's predicted values with the actual target values. It computes the prediction errors, squares them, and returns their average as a floating point number. A lower value means the model's predictions are closer to the real data. The batch gradient descent function optimizes model parameters by starting them at 0 and updating them over a set number of epochs. In each epoch, it compares predictions with the true values, computes the gradient from those errors, and adjusts the parameters using the learning rate. It also calculates the mean squared error after each update and stores these loss values. At the end, it returns the losses as a record of how the model improved over time. The model is trained for 60 epochs using batch gradient descent with 3 learning rates to compare training behavior. A rate of 0.08 should converge well, 0.005 should learn slowly, and 1.05 is high enough to show divergence. The loss values from each run are then used to compare how the learning rate affects training. The output first reports the NumPy version to support reproducibility. It then compares starting and ending loss values for healthy and slow learning rates to show how much the error decreases. For a divergent learning rate, the final loss is shown in scientific notation to emphasize rapid growth. Overall, a loss that falls and then levels off suggests the model is converging reasonably well. The plot compares 3 learning curve behaviors using clearly labeled lines. Reasonable convergence shows a healthy learning rate. Slow learning shows a rate that is too low, and divergence shows a rate that is too high, leading to unstable training. The plot is formatted to show gradient descent learning trends clearly. The y-axis uses a logarithmic scale to compare errors across large ranges, while the x-axis shows epochs and the y-axis shows mean squared error. A clear title identifies the graph as Learning Curve Trends for Gradient Descent. To make the gradient descent learning curves easier to interpret, we add a grid for reference, include a legend to identify each learning rate, and adjust the layout so the plot elements do not overlap. The finished plot is then displayed for visual comparison of the learning curve trends. This script uses synthetic beam measurement data to show how learning rate affects batch gradient descent. It standardizes the input, adds an intercept, and tracks mean squared error for 3 training cases. A moderate learning rate produces steady convergence. A small learning rate improves very slowly, and a large learning rate causes the loss to grow and diverge. The printed losses and logarithmic learning curve make the contrast between healthy, slow, and unstable training clear. Divergence detection. Training divergence occurs when a model moves away from a good solution instead of improving. In a healthy learning curve, loss generally decreases over time with only small fluctuations from stochastic updates. If the loss keeps rising or becomes highly erratic, the updates are likely too aggressive, causing the model to amplify errors rather than reduce them. Training can diverge when the learning rate is too high, but instability can also come from poorly scaled features or outliers. Large feature differences can make updates uneven, while unusual data points can cause sudden large errors, especially in stochastic gradient descent. Occasional spikes in the learning curve may be noise, but persistent growth, strong oscillations, or very high loss values usually mean training is failing. To diagnose divergence, look at the learning curve and the training setup. If loss rises immediately, the learning rate is likely too high. If it falls and then spikes, check the learning rate, feature scaling, and data quality. Compare several runs rather than trusting one plot. And if divergence appears, pause training and investigate whether the issue comes from stochastic updates, scaling, or implementation errors. Python code, divergence detection. Use linear regression to show how training can diverge when the learning rate is too aggressive. Compare it with a safer learning rate and examine the learning curves for warning signs that the model is not converging properly. We start by importing tools for numerical computing and visualization. NumPy supports efficient array operations and math, while Matplotlib's plotting module helps display results. Together, they prepare the environment for analyzing and visualizing divergence detection. A fixed seed is used with NumPy's random number generator, so the example produces the same random values every time it runs. This makes the results repeatable, which helps with debugging and consistent comparisons. We create a force measurement sequence in newtons using NumPy's linear spacing function. It produces 40 evenly spaced values from 10 to 100, forming the mechanical feature used for analysis. Deflection is calculated from force using a simple linear relationship. Multiply the force by 0.42 and add 3. To make the data more realistic, random measurement noise is added from a normal distribution with mean 0 and standard deviation 2. The result is a simulated deflection dataset that includes typical real-world variability. To standardize the force data, first find its average value and how much the values vary around that average. Then subtract the average from each force value and divide by the standard deviation. This gives the data a mean of 0 and a standard deviation of 1, making it easier to compare and use in machine learning. Before running regression, confirm that the scaled features and deflection measurements match in shape, so each force value pairs with the correct deflection value. Also make sure there are at least 10 data points, giving enough information for reliable analysis and model training. This function computes mean squared error loss for a linear regression model. It first predicts values using the slope, input values, and intercept, then compares those predictions with the actual values. The result is the average of the squared errors returned as a float to give one consistent measure of prediction accuracy. The function starts the linear regression model with the slope and intercept set to 0. It also creates a place to record the mean squared error during gradient descent. This lets the model update its parameters over time while tracking how the error changes. In each loop step, the model uses the current slope and intercept to predict the outputs, then compares those predictions with the actual values to find the errors. It then computes the slope gradient from the average relationship between the errors and the input values. This gradient shows how the slope should be adjusted to reduce error in the next iteration. The update step uses the error gradients to improve the model. The intercept gradient is found from twice the average error. Then both the slope and intercept are adjusted by moving against their gradients using the learning rate. After each update, the current mean squared error is saved, so the training loss can be tracked over time. The function returns the losses as a NumPy array, making them easy to analyze or manipulate with NumPy tools. This format also supports further processing or visualization, such as checking a learning curve to understand whether gradient descent is converging or diverging. We train a linear regression model with batch gradient descent using 2 learning rates for the same number of iterations. A smaller rate of 0.08 represents a safer choice, while a larger rate of 1.15 is more aggressive. The recorded losses from both runs are then compared to show how learning rate affects convergence. The divergence flag function checks whether training loss appears to be diverging. It flags a problem if any loss value is not finite, if the final loss is more than 5 times the initial loss, or if the loss increases in more than 20 steps. Together, these checks identify unstable training behavior, such as invalid values or sustained loss growth. We compare the safe and aggressive learning rate runs by printing their final losses, using standard formatting for the safe run and scientific notation for the aggressive run, to show any large divergence. Then we apply a divergence check to each loss curve to see whether either run became unstable. This lets us quickly compare both performance and training stability. This plot compares learning curves for a reasonable learning rate and one that is too large. The mean squared error is shown on a logarithmic scale across gradient descent iterations, making changes in error size easier to see. Labels, a title, a legend, and a light grid make the comparison clear, helping reveal when an aggressive learning rate causes divergence. This script shows how gradient descent can diverge in linear regression when the learning rate is too large. It creates noisy synthetic measurement data, scales it, and compares a safe learning rate with an aggressive one by tracking mean squared error over time. The safe rate steadily reduces the loss, while the aggressive rate makes the error grow sharply, signaling divergence. The results are printed and plotted on a logarithmic scale to make the contrast clear. Slow learning. Slow learning means the training error is decreasing, but much more slowly than expected. It is not divergence because the error is not exploding, and it is not normal convergence because progress is too gradual. In linear regression, this often suggests the parameter updates are too small, so optimization is working, but training is inefficient. Slow learning can occur when the learning rate is too low, so the model makes only very small updates each time. This is especially costly in batch gradient descent, where each update uses the full dataset but may reduce error only slightly. Training can also be inefficient when input features have very different scales, causing gradient descent to take a slow, indirect path toward the minimum. Feature scaling helps avoid this problem before training begins. To diagnose slow learning, look at how fast the error decreases over many updates, not just whether it decreases at all. If the error stays too high, you may need to adjust the learning rate, scale features, check for outliers, or use a different gradient descent method. Do not mistake this for the normal slowdown near convergence, where progress naturally flattens as the model approaches a good solution. The key question is whether the remaining error is acceptable, making learning curves useful diagnostic tools rather than simple progress trackers. Python code, slow learning. Slow learning uses small but useful updates during training. By comparing 2 learning rates, we can see how the choice affects progress. and learning curves make the training speed easier to understand. The script begins by importing two key libraries, NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. Together, these libraries provide the foundation for analyzing data and displaying results graphically. To make the example produce the same results every time, we set up NumPy's random number generator with a fixed seed of 7. This makes the random values predictable, which helps with debugging and comparing runs. We create a force feature measured in newtons by generating 40 evenly spaced values from 10 to 100 using NumPy's linspace function. This provides a simple set of simulated force measurements for later mechanical engineering analysis. Random measurement noise is generated with an average of 0 and a standard deviation of 0.8, matching the number of force readings. Deflection in millimeters is then modeled as a linear response to force by multiplying the force by 0.45, adding 3, and including the noise. This creates a simple mechanical behavior model with realistic random variation. To standardize the force data, first find the average force and how much the values vary around it. Then, adjust each value by subtracting the average and dividing by the standard deviation. This gives the feature a mean of 0 and a standard deviation of 1, which helps make gradient descent more stable during optimization. The program checks that the scaled feature vector and deflection measurements have matching lengths before continuing. This prevents later calculation errors, since the following operations depend on each feature value lining up with a corresponding measurement. This function measures prediction accuracy using mean squared error. It first makes predictions with a linear model using a slope and intercept, then compares them with the actual values. The result is the average of the squared differences, giving one number that summarizes how far the predictions are from the true values. The batch gradient descent function runs silently while setting up the optimization process. It begins with the slope and intercept set to 0, stores loss values to track progress, and counts the number of target values so the gradients can be calculated correctly. Inside the loop, the model predicts deflection by combining the current slope with the scaled input values and adding the intercept. It then compares these predictions with the actual measurements to find the errors. The slope is updated using a gradient based on the average product of the errors and input values, which shows how the slope should change to reduce the overall error. The model updates its slope and intercept using their gradients and the learning rate, moving both values in the direction that reduces error. The intercept gradient is based on twice the mean error, while the slope is adjusted using its own gradient. After updating both parameters, the mean squared error is recalculated and stored so the loss can be tracked across iterations. The function returns the loss history as a NumPy array, along with the final slope and intercept learned by gradient descent. This gives the caller both the training progress and the final parameters of the linear model. We compare learning rates by first running batch gradient descent with a slow learning rate of 0.001. The model trains for 120 iterations on the scaled features and deflection measurements, returning the loss history along with the final slope and intercept. These results help show how a small learning rate affects convergence speed and model accuracy. We run batch gradient descent on the scaled features and deflection measurements using a larger but safe learning rate of 0.08 for 120 steps. The process returns the loss history along with the final slope and intercept of the linear model. These results let us compare this reasonable learning rate with a slower one. To compare the two learning rates, we measure how much the mean squared error drops during training by subtracting the final loss from the initial loss. Doing this for both the slower and faster learning rates shows which one reduced error more effectively over time. We compare the final mean squared error for a slow learning rate and a more reasonable one to judge model performance. We also compare how much the error drops from start to finish in each case. The reasonable learning rate should reduce the error more effectively, showing why choosing an appropriate learning rate matters. Set up a clear plotting area, then compare two learning curves, one for a learning rate that is too small and one for a more reasonable rate. This shows how the model's error changes over time and makes it easier to see that an appropriate learning rate can lead to faster convergence. The plot is labeled to show batch gradient descent iterations on the x-axis and mean squared error on the y-axis. Its title highlights the comparison between slow learning and reasonable convergence, while the legend distinguishes the learning curves for the two learning rates. To finish the plot, turn on a lightly transparent grid so the data is easier to read without cluttering the view. Then apply a tight layout to prevent labels and plot elements from overlapping. Finally, use the show function to display the completed plot. This script shows how learning rate affects gradient descent in a simple linear regression model. It uses noisy synthetic data relating force to deflection, standardizes the feature, and compares a very small learning rate with a more reasonable one over repeated batch updates. The mean squared error is tracked throughout, showing that the tiny learning rate reduces error slowly, while the larger rate converges much faster. The printed results and learning curve plot highlight the difference in final error and overall improvement. In this lecture, you learn to explain gradient descent as repeated parameter adjustment to reduce prediction error, implement batch and stochastic gradient descent for linear regression from scratch, and analyze learning curves to diagnose slow learning, divergence, and reasonable convergence. In the next module, Module 5, we will go over none.
Thank you for your attention. See you all in the next lecture.